Good, gummisnood. And we are going to now jump away to the next person, and we're going to take her up on stage. So I hope you are ready to give her all the love. It's from the Swiss Youth and Science from Switzerland. We're talking about Elena Su.
Thank you. Okay, good. Hi everyone, my name is Elena and I'm a medical student at the University of Zurich in Switzerland. Within the frame of a high school project, I got the opportunity to join a research group studying Parkinson's. But before we get into that, I want to start with a bit of theory first. Parkinson's disease is the second most common neurodegenerative disorder after Alzheimer's disease. Typical motor symptoms affect gait, mobility, postural control, and balance. Typical non-motor symptoms include cognitive impairments and autonomic complications, among many others. It is assumed that roughly 0.3% of the global population is affected by Parkinson's disease, and this prevalence is expected to increase with growing life expectancy. Here in Sweden, it is assumed that something between 15 and 20,000 people suffer from Parkinson's. Although the definitive etiology of the disease remains unknown, two pathological hallmarks have been identified. First, the death of certain neurons, that's called neurodegeneration, and second, the intracellular inclusions, formation of inclusions of the protein alpha-synuclein, which will be the focus of my project as well. So, alpha-synuclein is a highly soluble presynaptic protein found in healthy vertebrate brains. It is proposed that during a pathogenic process, single alpha-synuclein proteins misfold, accumulate, and form large insoluble alpha-synuclein fibrils and acquire neurotoxic properties along the way. The underlying triggers of misfolding and the formation of inclusions are unknown, as well as the way these inclusions are transported within the brain. So, as with many other diseases, the field of Parkinson's disease research relies on experimental animal models in order to gain a greater insight into the disease progression. My project aimed to contribute to this ongoing effort. I tried to clarify to what extent the cerebellum is affected by the accumulation of alpha-synuclein in a specific transgenic mouse model of Parkinson's disease called THY1 human wild-type alpha-synuclein. To some extent, that specific transgenic mouse model recreates the formation of alpha-synuclein inclusions and the transportation to various brain regions. But although that mouse model is quite commonly used nowadays, its cerebellum has never been investigated in that regard before. So the method I performed is called immunohistochemistry. It can be used on a sample tissue to detect a target antigen, in this case alpha-synuclein, by using two antibodies. Thereby, the secondary antibody was labeled with an enzyme that later gave the stained brain sections a brownish color. The ideal immunohistochemistry protocol must ensure that the majority of the target is detected, while the level of unspecific bindings, that's called noise, remains low. To enable an accurate analysis of my results, 3 pilot studies were conducted to optimize the immunohistochemistry protocol for the given mouse model. So what we did was the following. We took brains of mice that were injected with preformed alpha-synuclein fibrils and injected them into the striatum. That's a nucleus in the forebrain, and then we examined their cerebellum. That's a major part of the hindbrain. And to investigate the formation of a potential pathology that spreads throughout the brain and with time, we had a look at 2 different time points. The early time point cohort consisted of brains that were collected roughly 4 months after the injection, and the late time point cohort of those 7 months post-injection. And then all sections, including positive and negative controls, were stained based on my immunohistochemistry protocol. So let's have a look at some results. First, just focus on the picture on the left, the early time point section. And if you look closely, you can see so-called neuritic staining patterns. And this, obviously, first of all, suggests that the alpha-synuclein pathology can be found in the cerebellum, because remember, the initial injection was made into the striatum, plus there were no such signals on the negative control. The latter then also indicates that the alpha-synuclein pathology must have spread within the brain. Now let's move on to the late time point section on the right. And obviously there are a few things that we can observe. First of all, the distribution of the staining patterns increases with time. On the right picture, it's much more widespread. Secondly, the intensity is significantly increased. This suggests that over time, the amount of accumulated alpha-synuclein in general becomes bigger. And third, the staining patterns appear in a differently shaped form. And when you look closely here on the left, in the early time point section, the staining patterns are much more linear and also rather dotted, while in the late time point section, the signals are much more clear, intense, but also rather branched and angular. So to sum this all up, the propagation and time-dependent spread of the alpha-synuclein pathology in the brains, in the cerebellum, of the THY1 human wild-type alpha-synuclein mouse model could be demonstrated. Still, it remains open as to how this transportation took place, and if the signals we see here only consist of the alpha-synuclein that we injected, but maybe also of alpha-synuclein that was normally found in the mouse brain. Nonetheless, the data obtained support the notion that the cerebellum might be more strongly involved in Parkinson's disease than previously thought. So it is up to you and I to further dig into the wide field of Parkinson's disease research, to find and test new drugs, to enhance treatment, or even find a cure for Parkinson's disease. Thank you.
Elena! Amazing, thank you. I have a quick question for you, Elena.
Yeah.
For people who is sitting here and is thinking, I want to be like Elena, I want to go med school, what do you want to say to those in the audience who are thinking like that?
Go for it. It's great. It's a lot of fun, and the reason I chose medicine and not life sciences was that as much as I love science, I wanted to have a more one-on-one impact on people's lives and just be nearer to patients and help them improve their lives. But anyway, there are so many different ways of helping people, helping society. Definitely go into research or into medicine. It's great.
And you are great. Thank you so much, Elena.
Thank you.
Thank you. I'll take this.
Whatever.
I'll take this one, Australia.
Take this. Thank you.
Amazing, Elena!